Lie back in your bed. Feel the weight of the day settle down. Let your body soften against the sheets. Close your eyes and listen to the quiet of the night around you. Imagine, if you can, the vastness of the ocean, stretching far beyond what your mind can reach, carrying warmth that slowly, quietly changes the world. Subscribe to catch a new documentary every night and drop a comment telling us where you're tuning in from. By the way, what time is it over there? Okay, just one last question before we get started. What happens when this immense, deep body of water begins to heat faster than scientists had expected? How does this heat move, and what does it mean for the life it holds and the land it touches? The ocean covers more than 70% of the Earth's surface. It holds more heat than all the air and land combined. In this way, it is both a buffer and a record, storing the energy from the sun and from the greenhouse gases humans release. Scientists measure the energy in the ocean as heat content. The deeper layers hold heat for centuries. The surface responds more quickly. In recent decades, instruments show that the heat content is rising faster than predicted, especially in the upper 2,000 meters. This increase is subtle at first. 1,000th of a degree may seem small, yet when multiplied by the vastness of the water, it becomes enormous, adding trillions of joules of energy to the oceans each year. Measuring this heat is not simple. The ocean is large, deep, and constantly moving. Traditional ship-based observations give detailed readings at single points, but they cannot cover the entire ocean. To track the heat more accurately, scientists have deployed networks of robotic floats called Argo. These floats sink and rise, taking measurements of temperature, salinity, and pressure at different depths. Satellites measure the surface temperature, observing tiny changes in the warmth of the water. Together, these instruments provide a continuous record. They reveal that the upper 2 kilometers of the ocean are warming faster than the deep ocean, but even the depths below show measurable increases. The heat does not spread evenly. The surface layers absorb sunlight directly, while winds and currents mix this heat through the upper ocean. Below, heat moves more slowly, layer by layer, passing through the thermocline, a boundary between warm surface water and the cold, deep water. Here, the transfer is governed by small movements, the slow sinking of dense water, and the occasional mixing caused by storms or eddies. Even in calm regions, heat gradually penetrates downward, changing the density and stability of the water. Each layer responds differently. The upper ocean heats quickly, expands, and can affect local sea level. The deeper layers are like a memory, holding the signature of warming from decades past. Recent measurements show that the rate of ocean heating is accelerating. The upper ocean absorbs more than 90% of the extra energy trapped by greenhouse gases. This means that while the air warms by a degree or two over decades, the ocean absorbs far more energy, but the change is slower to notice. Yet small changes have large effects. Warmer water expands, contributing to rising seas. Warm layers can also reduce the oxygen levels in the water, affecting marine life. This warming is not uniform. Certain regions heat faster due to the movement of currents, the angle of sunlight, and seasonal changes. The tropical oceans show consistent warming at the surface, while polar regions are seeing stronger warming below the ice, where currents bring heat toward the poles. The physical properties of water play a role. Water has a high heat capacity, meaning it can store large amounts of heat without changing temperature quickly. This makes the ocean a strong buffer for climate change, but also a slow responder. When energy enters the ocean, it spreads slowly, layer by layer, and only gradually affects the global climate system. The upper layers, which are well mixed by wind and waves, react faster. The mixed layer, typically 100 meters deep but varying by season and location, responds within months to years. Below, the thermocline slows the transfer. The deep ocean, thousands of meters below, responds over decades to centuries. The ocean's currents are vital in moving this heat around the globe. The Gulf Stream in the Atlantic carries warm water northward, while cold water returns southward at depth. In the Pacific, the equatorial currents distribute heat along east and west. These currents are influenced by winds, the rotation of the Earth, and the temperature and salinity of water. Heat is not only stored, but also transported, changing regional climates. For example, Europe's climate is warmer than it would otherwise be because the Gulf Stream brings warm water northward. The slowing or strengthening of these currents can affect the distribution of heat, sometimes amplifying the warming in certain regions. Seasonal cycles also affect how heat accumulates. In summer, the ocean absorbs more energy, the surface temperature rises, and the mixed layer expands. In winter, winds and storms mix the upper layers, redistributing heat downward. The cycle is complex and continuous. Even in calm conditions, the water is never still. Tiny currents, turbulence, and internal waves move heat quietly through the layers. Instruments detect these subtle movements, showing that the ocean is alive with slow, persistent changes, carrying energy across thousands of kilometers without interruption. Polar regions are particularly sensitive. The Arctic Ocean warms faster than the global average. Ice cover reduces, allowing more sunlight to enter the water. As the ice melts, fresh water mixes with salty ocean water, changing the density and altering currents. In the Antarctic, the process is slower but significant. Warm water reaches beneath ice shelves, slowly melting them from below. Scientists have observed this in the Amundsen Sea, where ice loss contributes to sea level rise. These regions act as early warning systems, revealing the consequences of accumulated heat before they become visible elsewhere. The measurements of ocean warming are precise, yet humbling. Scientists can detect temperature changes of a few hundredths of a degree. These small increments, multiplied over the vast volume of the ocean, represent enormous energy gains. The ocean absorbs roughly 200 zetajoules of heat per year, equivalent to the energy released by millions of Hiroshima-sized atomic bombs. This energy affects the density, currents, and even the chemistry of seawater. Each increase in heat is a step toward changes that can influence the climate, sea levels, and ecosystems worldwide. The ocean is a living record of our changing planet. Its layers, currents, and temperature profiles capture the impact of greenhouse gases. Each float, each satellite measurement, each scientific calculation adds to our understanding. The upper layers show recent trends. The deep ocean reveals the memory of past centuries. Heat spreads slowly, yet persistently. It is stored, moved, and measured with precision. And while the change may feel gradual, it is relentless, shaping the world around it in ways both visible and hidden. The ocean carries the energy of a warming planet quietly, but without pause, reminding us of its immense scale, its capacity, and the consequences that will follow. The sunlight reaches the surface of the earth in steady, invisible waves. Some of it warms the land, some warms the air, and much of it reaches the ocean. The ocean absorbs energy slowly and steadily, holding it in the layers of water, carrying it across vast distances. The process of warming begins in the atmosphere. Greenhouse gases, like carbon dioxide and methane, surround the Earth, forming a thin layer that traps some of the heat the planet radiates back into space. Without this layer, the Earth would be much colder. With it thickening, more heat stays near the surface, building slowly over time. Each molecule of gas holds a small part of this energy. Together, they act like a blanket over the planet, reducing the loss of warmth and keeping more energy in the system than would occur naturally. The result is subtle at first, a slight increase in global temperature, but it is persistent, continuous, and measurable. The energy trapped by greenhouse gases does not stay only in the air. It moves into the oceans, the largest heat reservoir on the planet. The interface between air and water allows heat to pass through. The sun warms the ocean directly, but the atmosphere transfers additional energy as well. Winds stir the surface, waves create friction, and small eddies move the warmed water across hundreds of kilometers. Some energy enters the mixed layer, the uppermost part of the ocean, where water is well mixed by wind and waves, often extending down 100 meters. In this layer, heat is absorbed quickly, distributed through currents, and carried across regions. The ocean's surface temperature reflects the combination of sunlight, atmospheric energy, and heat moved from other areas. Below the mixed layer lies the thermocline. This boundary separates the warmer surface water from the colder deep ocean. The thermocline is not static. It shifts with the seasons, with storms, and with large-scale currents. Heat moves more slowly through the thermocline because the water is more stable. Denser cold water below resists mixing with the lighter warm water above. Yet over months and years, heat penetrates downward, layer by layer, slowly warming the deeper ocean. The deep ocean itself, thousands of meters below the surface, responds even more gradually. Here, heat accumulated today may remain for centuries, carried by slow currents that circulate around the globe. In this way, the ocean acts as both a sponge and a memory, holding the energy that humans release into the atmosphere over generations. The differences between land and water are striking. Land absorbs sunlight quickly, warming the surface fast. Air above the land heats as well, creating convection currents that rise and fall with the day and night. Water behaves differently. Because of its high heat capacity, it requires much more energy to raise its temperature. A small patch of land may become hot in a single afternoon, but the same energy spread over a cubic kilometer of ocean produces only a subtle rise in temperature. The ocean's density allows it to store this energy for long periods, distributing it gradually through currents and mixing processes. The result is a slow, steady increase in heat that can be tracked over decades, revealing patterns that would be invisible in the rapid fluctuations of the air. The mechanics of heat transfer into the ocean are continuous yet variable. The surface absorbs energy most quickly during the day, but night does not stop the process. Winds continue to mix the water, currents continue to move heat horizontally, and storms redistribute warmth through the upper layers. Seasonal changes alter the intensity and location of heating. In the tropics, sunlight is direct and consistent year-round, creating a steady warming of surface waters. Toward the poles, the angle of sunlight varies with the seasons, creating periods of strong warming in summer and slow cooling in winter. These regional differences create gradients, driving currents that transport heat across the globe, linking distant oceans in a vast network of energy flow. The mixed layer itself is dynamic. It thickens in the winter when storms churn the surface, deepening the layer of well-mixed water. In summer, it becomes shallower, isolating the surface from the cooler layers below. Within the mixed layer, heat is shared quickly. Water moves in large and small patterns, from gentle eddies to large-scale gyres. These movements are essential for distributing energy, preventing the surface from becoming much hotter than the layers below. The thermocline below acts as a slower conveyor. Heat penetrates gradually, creating a buffer between the warm surface and the cold, deep ocean. In this way, the ocean regulates the speed of warming, storing energy in a manner that smooths out sudden changes in the climate system. The deep ocean remains a slow but crucial player. Currents carry water that has been warmed at the surface to distant regions and depths. Water sinks in polar regions where it becomes dense due to cooling and increased salinity, then flows along the ocean floor toward the equator. This circulation moves heat, nutrients, and oxygen, linking surface warming to the deepest layers. The result is a complex but orderly system in which heat is constantly redistributed. Though changes in the deep ocean are slow, they are significant. The energy stored in these layers can influence climate over decades to centuries, affecting weather patterns, sea level, and the strength of currents worldwide. The process of warming is affected by the properties of water. Water's ability to store heat without large temperature changes allows the ocean to absorb a vast amount of energy while remaining relatively stable. This property also means that surface warming may lag behind the total energy increase. Seasonal fluctuations, storms, and currents all interact with the heat capacity to create subtle but measurable changes. Even small changes in temperature can alter the density of water, which in turn affects currents, mixing, and heat transfer. In this way, the ocean responds both to the amount of heat absorbed and to the physical structure of its layers, producing a feedback loop that shapes the pace of warming. Heat transfer into the ocean is also influenced by interactions with the atmosphere. Warm air temperatures increase evaporation, moving energy from water into the air. Conversely, cooler air can draw heat from the ocean back into the atmosphere. Clouds, humidity, and wind speed all modulate this exchange. In regions with strong winds, such as the Southern Ocean, the mixed layer is deeper, allowing heat to penetrate more efficiently. In calmer tropical waters, the surface absorbs energy more slowly, and the thermocline acts as a barrier to rapid warming. These interactions between air and water create a constantly shifting pattern of energy distribution, making ocean warming both predictable in its general trends and variable in its regional expression. Scientists measure the pace and mechanics of warming through observation and modeling. Argo floats record temperatures from the surface to 2 kilometers deep, giving a three-dimensional view of energy distribution. Satellites track sea surface temperatures and measure changes in the ocean's energy budget. Together, these tools reveal that warming is concentrated in the upper layers but steadily moving downward. Observations confirm that the thermocline moderates the transfer of heat, while deep currents carry energy to distant regions. Heat is stored, moved, and released in a continuous cycle, linking the atmosphere, the surface ocean, and the deep ocean in a complex yet orderly system. The ocean's warming is subtle but persistent. Each day, it absorbs energy that is trapped by greenhouse gases. The surface responds first. The mixed layer distributes heat horizontally and vertically, and the thermocline and deep layers store it for the future. Differences between land and water emphasize the ocean's role as a slow, steady buffer. Currents and mixing move energy across distances, while the high heat capacity ensures gradual change. Together, these processes form the mechanics of warming, a natural yet human-influenced system that carries the mark of our emissions through time, hidden beneath the waves but measurable by those who study it carefully. The ocean warms quietly, layer by layer, holding the heat and spreading it slowly, a reminder of the invisible forces that govern our planet and the steady influence of human activity. The ocean does not warm evenly. Across its vast expanse, some regions heat faster, while others change more slowly. The Pacific, Atlantic, and Indian Oceans each show distinct patterns of warming, influenced by currents, winds, and sunlight. In the Pacific, the equatorial waters absorb energy steadily throughout the year. The trade winds push warm surface water westward, piling heat against the islands of Indonesia and the Philippines. In the eastern Pacific, near South America, the water is cooler, drawn up from the depths by upwelling currents that bring cold water to the surface. These movements create gradients in temperature, with warm and cool patches shifting gradually with the seasons. The Pacific is also home to the El Niño and La Niña cycles, which temporarily redistribute heat across thousands of kilometers. During El Niño, warm water spreads eastward, changing weather patterns and temporarily raising surface temperatures across large regions. La Niña has the opposite effect, with cooler waters dominating the central and eastern Pacific. These cycles influence the local pace of warming, but do not alter the long-term trend. Overall, the Pacific absorbs a substantial portion of the planet's extra heat, yet this absorption is uneven, shaped by winds, currents, and seasonal variation. The Atlantic Ocean shows its own pattern. Warm water from the tropics moves northward along the western boundary, carried by the Gulf Stream. This current is a powerful conveyor of heat, moving water from the Caribbean and Gulf of Mexico toward the North Atlantic. As the water travels north, it releases heat into the atmosphere, warming Europe and influencing weather far beyond the ocean itself. The Gulf Stream then dives beneath the surface in the North Atlantic, where it becomes colder and denser, returning southward as deep currents. This movement carries heat away from the surface, influencing both the warming rate of local waters and global circulation. In the subtropical Atlantic, surface warming is steady, while the North Atlantic exhibits slower warming at the surface because of the mixing and transport of heat downward. Seasonal changes create cycles of warming and cooling, but the long-term trend remains upward, with the overall heat content of the Atlantic rising steadily over decades. The Indian Ocean behaves differently. It is largely enclosed by land, bordered by Africa, Asia, and Australia. Winds change direction seasonally, creating the monsoon system. During the summer months, strong winds push warm surface water toward the west, while cooler water rises in the east. These movements distribute heat unevenly, concentrating it in some regions while leaving others relatively cooler. Despite the seasonal variation, the Indian Ocean shows consistent warming over the years, particularly in the upper layers. The enclosed nature of the basins slows some of the deep mixing, allowing surface waters to retain heat longer. Currents such as the Agulhas and Leeuwin carry this energy along the coasts, linking warming patterns across distant regions. The Indian Ocean's warming is a combination of steady accumulation and seasonal redistribution, making it a unique example of regional variation in ocean heat uptake. Currents play a central role in shaping these regional differences. The Kuroshio Current in the Western Pacific carries warm water northward along the coast of Japan. This current distributes heat along the western boundary, influencing both the local climate and the transport of energy to higher latitudes. Similar western boundary currents exist in other oceans, including the Gulf Stream in the Atlantic and the East Australian Current in the Pacific. These currents carry warm water from the tropics toward the poles, while returning cold, dense water flows at depth toward the equator. The movement of heat by these currents creates a dynamic pattern of warming that is more complex than simple surface measurements might suggest. Heat is constantly in motion, moving from one region to another, sometimes concentrating, sometimes dispersing, but always adding to the global energy of the oceans. Polar regions are warming faster than the tropics, a phenomenon known as polar amplification. In the Arctic, summer ice retreats each year, exposing dark water that absorbs sunlight more efficiently than reflective ice. This absorption accelerates warming locally. The warming in the Arctic is not uniform. Shallow seas such as the Barents and Chukchi experience faster changes than the central Arctic basin. Seasonal ice cover changes also modulate the heat uptake, with open water absorbing more energy during summer months. In the Antarctic, the situation is slower but still significant. The Southern Ocean circulates around the continent, mixing surface waters and deep currents. Ice shelves are slowly melting from below as warmer water penetrates beneath them, and surface warming occurs in localized zones where currents bring heat from other regions. Polar amplification demonstrates that latitude plays a critical role in the rate of warming, with high-latitude regions responding more quickly to global energy changes than equatorial areas. Equatorial regions, in contrast, experience relatively consistent warming throughout the year. The sun shines nearly directly overhead, providing steady energy. Surface temperatures rise gradually, but the strong thermocline in these regions slows the transfer of heat to deeper layers. Upwelling zones bring cooler water from below, moderating surface temperature increases and creating localized variations in warming. These processes combine to produce a more stable warming trend at the equator, in contrast with the amplified changes at the poles. The balance between steady absorption and vertical mixing determines the pace at which equatorial oceans accumulate heat, influencing the global distribution of energy. Seasonal variation further shapes regional patterns. During summer months, the surface absorbs more sunlight, raising the temperature of the mixed layer. In winter, cooling occurs at the surface, and storms mix heat downward into the thermocline. These cycles are evident in all oceans, but differ in magnitude depending on latitude and local climate. In tropical regions, seasonal swings are smaller, while mid-latitude and polar waters experience larger temperature changes between summer and winter. The mixed layer deepens in winter due to strong winds and storms, allowing heat to move downward, while it shallows in summer, isolating surface warmth from deeper water. Over decades, these seasonal patterns overlay a steady long-term increase in ocean heat content, producing a complex, layered record of warming across regions. Local geography and bathymetry also affect regional warming. Shallow seas warm faster than open ocean areas because there is less water to absorb incoming energy. Coastal waters may experience more rapid heating due to the reduced volume and the interaction with sunlight and atmospheric warming. Deep basins, on the other hand, moderate warming through slow mixing and heat storage. Ocean ridges, continental slopes, and submarine plateaus guide currents and influence the distribution of heat, creating hotspots and slower zones of warming. These physical features interact with the broader patterns of currents, winds, and seasonal cycles to produce a mosaic of temperature changes across the oceans. The Atlantic's north-south gradient provides a clear example of regional variation. Warm tropical waters move northward, while deep cold water flows southward. This movement not only transports energy, but also moderates the local warming rate. In the North Atlantic, the interplay between the Gulf Stream and thermohaline circulation ensures that surface warming is spread over a wide area, reducing extreme changes. In contrast, the South Atlantic, with slower currents and more enclosed basins, shows more concentrated warming in certain regions. The patterns in the Atlantic highlight how circulation systems, in combination with latitude and geography, define the local pace of warming. The Pacific Ocean illustrates the influence of oscillations. El Niño events redistribute warm water eastward, raising temperatures across vast areas. La Niña events bring cooler water to the same regions, temporarily reducing surface warming. Despite these cycles, the long-term trend remains clear. The ocean continues to absorb more energy each year. Currents, such as the North Equatorial Current and the South Equatorial Current, move warm water toward the west, where it accumulates against islands and coastal shelves, creating consistent regional differences. The Pacific's complex interplay of wind, current, and sunlight demonstrates how multiple factors interact to produce spatial variations in warming. The Indian Ocean demonstrates the effect of monsoon winds. Seasonal reversal of winds shifts surface waters, moving heat between eastern and western basins. Warm water accumulates along the western coast of India and East Africa during summer months, while cooler waters rise in the east. Currents, such as the Agulhas Current, carry warm water southward, linking the Indian Ocean to the South Atlantic. This regional connectivity shows that warming is not isolated, but influenced by movements across ocean basins. Even within a single ocean, variations in circulation, wind, and geography produce a patchwork of warming rates and energy accumulation. Taken together, the Pacific, Atlantic, and Indian Oceans reveal the complexity of regional warming. Equatorial areas warm steadily but moderately. Polar regions warm faster and are subject to amplification effects. Currents carry heat across vast distances, redistributing energy and moderating local trends. Seasonal cycles overlay long-term changes, while local geography, bathymetry, and upwelling zones create additional variation. The oceans are not a uniform reservoir, but a dynamic system, with heat moving, mixing, and accumulating in patterns shaped by natural processes. Understanding these regional differences is essential to predicting the future impacts of ocean warming, from currents to climate to the life that depends on the sea. In every basin, layer, and current, the ocean responds to the energy humans release, quietly recording the changes while continuing its endless circulation. The ocean's warming is not confined to its own waters. The heat spreads outward, touching the frozen edges of the planet. Ice sheets and glaciers sit on land, holding vast amounts of fresh water. Greenland in the north and Antarctica in the south contain the majority of this ice. When the ocean warms, it affects these frozen regions, even from a distance. Warm currents reach the edges of ice sheets, melting them from below. Surface warming in coastal areas accelerates ice loss at the margins. Each bit of ice that melts adds water to the ocean, raising sea levels. The process is gradual, measured in millimeters per year, but it continues steadily, adding energy and volume to the oceans in ways that are both visible and subtle. Greenland's ice sheet is especially sensitive. As the atmosphere warms, summer melting increases on the surface, and rivers of meltwater flow toward the sea. Ocean currents surrounding Greenland carry heat to the coastal regions, melting ice shelves from below. Scientists measure ice loss using satellites that track changes in elevation and gravity, revealing that Greenland has lost hundreds of billions of tons of ice in recent decades. This loss contributes directly to global sea level rise, roughly 1 millimeter per year from Greenland alone. The patterns are complex. Some regions of Greenland are losing ice faster than others, influenced by local weather, ocean currents, and the topography of the ice itself. The ice sheet reacts to both air and ocean temperature, showing that warming is interconnected across the planet. Antarctica is more massive and colder, yet it is not immune. The Antarctic ice sheet holds enough water to raise seas by over 50 meters if melted completely. The Southern Ocean circulates around the continent, and warm water occasionally reaches beneath ice shelves, slowly eroding them. The Amundsen Sea sector, in particular, shows rapid thinning of ice from below, driven by ocean currents carrying warmer water from the north. East Antarctica is colder and more stable, but even there, some glaciers are starting to flow faster into the sea as ice shelves thin. Satellite observations show that Antarctica, like Greenland, has been losing ice at an accelerating rate, contributing a similar order of magnitude to global sea level rise. The combination of surface melting and basal melting at the margins demonstrates that ocean heat drives change both above and below the ice. The contribution of melting ice to sea level rise is compounded by thermal expansion. Water expands as it warms. The upper ocean layers, which absorb the majority of excess heat, expand slightly, adding to the volume of the sea. Though each degree of warming causes only a small increase in volume, the vastness of the oceans multiplies the effect. Observations indicate that thermal expansion accounts for roughly half of the current sea level rise, with melting ice contributing the other half. This expansion is not uniform. Tropical oceans, which are warming steadily, contribute more directly to rising seas in nearby regions. Polar regions contribute less to expansion, but more through direct ice loss. Together, these processes create a global increase in sea level that continues year after year. Current data on sea level rise show a clear upward trend. Tide gauges and satellite measurements indicate that global mean sea level has risen by more than 20 centimeters since the late 19th century. The rate has increased over time. In the 20th century, the average rise was about 1.4 millimeters per year. In recent decades, the rate has doubled to over 3 millimeters per year. This acceleration matches the increasing heat content of the oceans and the observed ice loss from Greenland and Antarctica. Projections for the coming century vary depending on greenhouse gas emissions, but even moderate scenarios suggest an additional half-meter of rise by 2100. High-emission scenarios could produce a meter or more, particularly if ice sheet loss accelerates faster than current models predict. Sea level rise is not evenly distributed. Ocean currents, wind patterns, and the gravitational pull of large ice sheets influence the local height of the sea. When Greenland loses mass, the gravitational attraction it exerts on surrounding waters decreases, causing water to migrate toward the equator. As a result, sea level rise is higher in some regions than others. Coastal cities in the tropics, such as Jakarta and Manila, experience greater increases than northern cities at similar latitude. Likewise, changes in currents can raise or lower water along coastlines over short periods, superimposed on the long-term rise driven by heat and ice loss. These regional variations are critical for understanding the impacts on human settlements and ecosystems. The process is slow but continuous. Every year, the oceans absorb more energy. The mixed layer and thermocline distribute this heat downward, reaching polar margins. Ice shelves melt, glaciers accelerate, and seawater expands. The measurements collected by satellites, floats, and tide gauges provide a record of change. Greenland and Antarctica have lost ice at rates measured in hundreds of billions of tons per decade, and the upper ocean warms by fractions of a degree each year. Yet the cumulative effect is substantial. In addition, feedbacks amplify the change. As ice retreats, darker water or land is exposed, absorbing more sunlight and increasing local warming. As the ocean warms, its density changes, altering currents and redistributing heat. The system is interconnected, a continuous flow of energy, mass, and motion. Projections integrate multiple factors: atmospheric warming, ocean heat content, ice sheet dynamics, and thermal expansion. Climate models simulate how each component contributes to sea level rise. The results show that the next decades will bring steady increases. The rate of rise may accelerate if ice sheets become less stable or if warming exceeds current expectations. Even if emissions are reduced, the oceans will continue to warm for centuries, and ice sheets will respond slowly but persistently. The long memory of the ocean means that some sea level rise is already unavoidable, driven by energy that has already entered the system. The rising seas have broad implications. Coastal ecosystems, such as mangroves and salt marshes, are slowly inundated. Beaches erode more quickly as higher water reaches further inland. Low-lying islands and deltas face increased flooding, particularly during storms or king tides. Even small annual increases in sea level compound over time, gradually reshaping coastlines. Human settlements near the shore must adapt to these changes. Some regions rely on levees, seawalls, and drainage systems, while others face unavoidable relocation. The physical changes are visible, but the process remains largely gradual, measured in millimeters and centimeters each year, a silent yet persistent reminder of the ocean's warming. The mechanisms of melting and expansion are interconnected. Warmer water reaches the ice margins, melting from below. Surface melting accelerates glacier flow, sending more ice into the sea. Heat spreads through the upper ocean, causing expansion. Currents carry energy from the tropics to the poles, amplifying the effect in vulnerable regions. Observations confirm that these processes are already underway, and modeling suggests they will continue and intensify. The rise of the sea is both a consequence and a signal of ocean warming, a measurable output of the energy absorbed by the planet. Each new record of sea level rise reflects the cumulative action of melting ice and thermal expansion across decades. The feedbacks reinforce themselves over time. Ice loss exposes darker surfaces, which absorb more sunlight. Warmer oceans erode glaciers, which in turn release more fresh water into the ocean, influencing density and currents. Thermal expansion increases the volume of water, raising the baseline for flooding and storm surge. The combination of these factors is evident in satellite observations, tide gauge records, and ocean heat measurements. Scientists track these changes carefully, noting that even small differences in temperature translate into significant impacts when multiplied by the scale of the ocean and the size of ice sheets. In this way, ocean warming links directly to rising seas. The heat stored in the upper layers moves poleward and downward, melting ice sheets and expanding water. Greenland and Antarctica are major contributors, losing ice at accelerating rates. Thermal expansion adds further volume. Measurements show a clear trend of global sea level rise, with projections indicating continued increases throughout the century and beyond. The process is gradual but relentless, connecting the invisible warming of the ocean to the visible changes along coastlines, shaping the world silently and steadily. Every fraction of a degree gained in the ocean's heat content results in measurable water rising, reminding us that the ocean's warming is both subtle and consequential, persistent and global in its reach. The ocean absorbs more than just heat. It takes in gases from the atmosphere, including carbon dioxide, a major driver of climate change. As levels of carbon dioxide rise in the air, the ocean absorbs more of this gas, acting as a buffer that slows warming in the atmosphere. Yet the process has consequences. When carbon dioxide dissolves in seawater, it reacts chemically to form carbonic acid. This lowers the pH of the water, making it more acidic. Scientists call this process ocean acidification. Even small changes in pH can have profound effects on marine life. The water becomes more corrosive to organisms that build shells or skeletons from calcium carbonate. Corals, shellfish, and microscopic plankton are among the most vulnerable, their delicate structures slowly weakened by the changing chemistry. Warming and acidification are linked in subtle ways. Warmer water holds less carbon dioxide than cold water, so in some regions, increased surface temperatures reduce the immediate uptake of gas. Yet the ocean continues to absorb carbon dioxide overall, and the combination of higher heat and chemical change creates a complex environment for marine life. The acidified water affects the ability of organisms to extract calcium and carbonate ions from seawater. Corals, which form reefs that support diverse ecosystems, grow more slowly in acidified conditions. Shellfish, such as oysters, mussels, and clams, struggle to maintain strong shells. Plankton, which forms the base of the food chain, may reduce shell formation, affecting the survival of species that rely on them for food. These effects are measurable and ongoing, appearing in laboratory studies and field observations alike. The Arctic and Antarctic are particularly sensitive to acidification. Cold water absorbs carbon dioxide more readily than warm water, meaning polar oceans experience faster chemical changes. In the Arctic, ice melt dilutes seawater, reducing salinity and further altering chemical balance. Acidified waters spread under ice shelves in Antarctica, reaching areas where specialized organisms depend on stable conditions. The polar marine ecosystems are home to species adapted to narrow ranges of temperature, salinity, and pH. As conditions shift, these species face stress, slower growth, and increased mortality. Even minor shifts in pH can ripple through the ecosystem, affecting predators, prey, and the balance of nutrients. Tropical regions experience acidification differently. Warmer surface waters absorb less carbon dioxide, but the sheer volume of water and steady atmospheric increase ensures that tropical oceans still see a gradual decline in pH. Coral reefs are concentrated in these regions, and they are highly vulnerable. Bleaching events, triggered by high temperatures, weaken coral structures, while acidification makes it harder for corals to repair damage. The combination of heat stress and chemical change reduces the resilience of reefs. Over time, coral growth slows and fragile structures erode. The reefs, which support thousands of species of fish, invertebrates, and algae, begin to lose complexity, altering habitats and food availability throughout the marine environment. Microscopic plankton respond to warming and acidification in ways that influence the entire ocean. Some species reduce calcification, producing thinner shells or no shell at all. Others may shift their distribution to find more favorable conditions. These changes affect food webs. Zooplankton, which feed on phytoplankton, may find less nourishment, reducing their population. Fish and larger predators that rely on these plankton may experience declines in abundance. The cascading effects can alter entire ecosystems, even in open ocean regions far from human activity. Scientists measure these effects by sampling water for pH, carbonate concentration, and species abundance, revealing clear trends over decades. The feedback loops between warming and acidification are significant. Warmer waters expand, transporting energy and nutrients to different regions, which can influence local biological activity. High temperatures may increase respiration rates in marine organisms, raising carbon dioxide locally and contributing to further acidification. Phytoplankton growth may change with temperature, altering the rate at which carbon dioxide is taken up and sequestered. These interactions create a dynamic system where chemical and physical changes amplify each other. The ocean is both absorbing heat and carbon, yet the consequences are increasingly evident in the form of stressed ecosystems and shifting species patterns. Shellfish provide a clear example of vulnerability. Oysters, clams, and mussels must maintain a delicate balance of ions to build their shells. Acidified water reduces the availability of carbonate ions, forcing organisms to expend more energy to maintain shell strength. In some cases, young larvae are unable to survive, reducing recruitment and population growth. These changes have practical consequences for fisheries, aquaculture, and food supply, as well as ecological effects. Predators that rely on shellfish for food must adapt, shift their diets, or face declines in population. The interconnectedness of species means that acidification has impacts far beyond the immediate area, gradually altering the structure of ecosystems. Coral reefs, which are often called the rainforests of the sea, illustrate both the direct and indirect effects of warming and acidification. Corals rely on calcium carbonate to build their skeletons, forming the three-dimensional structures that shelter countless species. Acidified waters slow calcification, reducing growth rates. Warming water increases the likelihood of bleaching, a process in which corals expel the algae that provide them with food and color. Bleached corals are weaker, slower to grow, and more susceptible to disease. Over time, reef structures may crumble, diminishing habitat complexity and reducing biodiversity. Fish populations may decline, and algae may take over, creating shifts in community composition. The consequences ripple outward, affecting predators, prey, and humans who depend on the reef for food or coastal protection. Plankton, though microscopic, play an equally vital role. Coccolithophores, tiny calcifying algae, form shells from calcium carbonate. Acidification reduces their ability to produce these shells, while warming may alter their growth and distribution. Since plankton forms the base of the food web, changes in their abundance and composition affect higher trophic levels, including fish, seabirds, and marine mammals. Nutrient cycles may also shift. For example, reduced plankton calcification may influence the export of carbon to the deep ocean, altering the ocean's role in global carbon storage. In this way, acidification interacts with ocean warming to affect not only the local environment, but also global climate regulation. Regions with strong upwelling, where deep, nutrient-rich waters rise to the surface, experience combined effects of warming and acidification. Upwelled waters are often colder and more acidic, meaning that surface organisms encounter stress from both temperature and pH changes. Coastal fisheries in these areas may notice reduced growth rates in key species, altered reproduction cycles, and changes in migration patterns. Scientists track these changes with chemical measurements, satellite data, and biological sampling, observing shifts that indicate the combined pressure of heat and chemical change. The interactions are complex but measurable, revealing that the ocean's chemistry responds to the energy humans release in tangible ways. The acidification process also creates feedbacks with the climate system. As calcifying organisms decline, their ability to sequester carbon diminishes. Coral reefs, plankton, and shellfish remove carbon from the water to build their structures, storing it in sediments or as part of the food web. If these organisms are stressed, less carbon is captured, leaving more in the atmosphere and surface ocean. This, in turn, can contribute to additional warming, completing a subtle but continuous feedback loop. In this way, warming and acidification are intertwined, each reinforcing the other through physical, chemical, and biological processes that span the globe. Scientists observe these changes through long-term monitoring programs. pH sensors, water sampling, and satellite observations track the chemical changes in seawater over time. Biological studies measure growth rates, reproductive success, and population trends in vulnerable species. The data show a steady trend of acidification in most oceans, with localized variation based on currents, temperature, and biological activity. Models project that if current carbon emissions continue, ocean pH may decline by an additional 0.3 to 0.4 units by the end of the century. The combined effect of warming and acidification suggests that many ecosystems will face significant stress, requiring decades or centuries to adapt. The ocean records both heat and chemistry. Warming and acidification occur together, each influencing the other. Coral reefs, shellfish, and plankton provide measurable evidence of these changes, reflecting subtle shifts in water chemistry and temperature. Feedback loops amplify impacts, affecting carbon cycles, species abundance, and food webs. The ocean is dynamic, absorbing energy and gas while simultaneously responding to them. Acidification is a silent transformation, occurring gradually beneath the surface, yet it has clear consequences for marine ecosystems and for the planet as a whole. A reminder that the ocean's chemistry is inseparable from the energy it absorbs and the life it sustains. The ocean moves in patterns that stretch across the globe. These currents carry heat, nutrients, and salt, linking distant regions and helping regulate climate. Scientists often describe them as the ocean's heartbeat, a rhythmic pulse that maintains balance between the tropics, the poles, and every ocean basin in between. Warm water flows from the equator toward the poles, while cold, dense water sinks and returns toward the tropics at depth. This system, known as thermohaline circulation, is driven by differences in temperature and salinity. It moves energy and mass slowly but steadily, shaping the climate for millions of people. Yet, as the ocean warms, these currents face subtle but significant changes. The Atlantic Meridional Overturning Circulation, or AMOC, is one of the most studied components of this system. Warm surface water from the tropics travels north along the eastern coasts of the Americas and Europe, carrying heat toward higher latitudes. As this water cools in the North Atlantic, it becomes denser and sinks, forming deep currents that flow southward. This process has been stable for thousands of years, providing a predictable transfer of energy from warm regions to cold. Warming alters this pattern. When surface water becomes too warm or too fresh, its density decreases. It does not sink as easily, slowing the downward flow that drives the AMOC. Observations over recent decades suggest that this circulation has already weakened compared to historical levels, indicating that the ocean's heartbeat is changing. Freshwater input from melting Greenland ice and Arctic glaciers further disrupts the AMOC. The influx of cold, low-salinity water reduces the density of surface water in the North Atlantic. Less dense water resists sinking, diminishing the strength of the overturning circulation. As a result, heat is not transported northward as efficiently, creating regional differences in temperature. Northern Europe and parts of North America may experience altered weather patterns, even cooling in some seasons, while the tropics could warm more rapidly. The circulation does not stop entirely, but its rhythm slows, altering the distribution of energy around the globe. Scientists track these changes with arrays of buoys, floats, and satellite data, revealing a steady but measurable weakening of the system that has persisted for decades. Other currents are influenced as well. The Gulf Stream, which is part of the AMOC, carries warm water along the eastern coast of the United States and across the Atlantic toward Europe. Its speed and strength are linked to the density differences that drive the overturning circulation. Slower sinking in the North Atlantic reduces the flow of the Gulf Stream, changing sea surface temperatures along the coasts it passes. This can affect regional weather, influencing rainfall, storm tracks, and even hurricane intensity. The ocean's currents are interconnected. A change in one region reverberates through the system, altering conditions thousands of kilometers away. The pulse of the ocean is both local and global, tying together distant climates in a single network of movement. Warming affects not only the Atlantic, but also the Pacific and Indian Oceans. The thermohaline circulation in the Pacific is slower, yet it still moves water and heat vertically and horizontally. Changes in surface temperature, salinity, and wind patterns influence the depth at which water sinks. modifying currents that carry energy across the basin. In the Indian Ocean, seasonal monsoon winds drive surface currents, which interact with thermohaline processes to move warm water toward the poles. All these systems are linked through global circulation, meaning that disturbances in one region, such as a weakening AMOC, can have ripple effects across oceans and continents. The consequences of disrupted currents extend beyond temperature. Nutrient transport changes as water slows or shifts course. Deep currents bring nutrient-rich water to the surface, supporting phytoplankton growth, which forms the base of the food chain. If overturning slows, less nutrient-rich water reaches the upper ocean, reducing productivity in some regions. Fish populations may decline or move, affecting human fisheries and marine ecosystems. The impacts cascade through the food web. Seabirds, marine mammals, and larger predators rely on consistent patterns of nutrient availability. Subtle changes in currents can therefore reshape ecosystems over time, even in areas far from the original disruption. Climate patterns respond in turn. Europe depends on heat transported by the Gulf Stream to moderate winter temperatures. If the AMOC slows, winters may become colder, while summers may bring heat waves elsewhere due to changes in atmospheric circulation. Rainfall patterns shift as moisture transport is affected, altering monsoon timing and intensity in Africa, Asia, and South America. Droughts may intensify in some regions, while flooding becomes more frequent in others. The ocean's heartbeat, once steady, now sends signals that reshape weather across the planet. Though the process unfolds over decades and centuries, the effects are measurable and increasingly evident in observational records and climate models. Even subtle weakening of thermohaline circulation can influence hurricanes and storms. Warm surface water provides energy for storms. If currents redistribute heat differently, regions of the tropics may experience warmer or cooler waters than expected. This affects the intensity and formation of storms. Some areas may see stronger hurricanes, while others experience reduced activity. The pattern is complex, tied to the rhythm of ocean heat transport and atmospheric interaction. Scientists analyze sea surface temperatures, current strength, and atmospheric pressure patterns to track these potential changes. Models suggest that continued warming and ice melt could amplify disruptions, with consequences that reach both coastal and inland regions. The ocean's pulse is evident in seasonal cycles as well. In winter, surface cooling typically strengthens sinking in the North Atlantic, maintaining circulation. In summer, warmer surface temperatures can slow sinking temporarily. Warming trends overlay these seasonal cycles, gradually altering the baseline. Each year, the pulses of sinking and rising water are slightly different, and over decades, the cumulative effect becomes significant. The ocean's rhythm, once predictable, now exhibits variation, demonstrating the sensitivity of currents to gradual heating and freshwater input. The long-term memory of the ocean ensures that changes persist, even if surface temperatures fluctuate over shorter timescales. Observations confirm that the ocean's heartbeat is changing. Buoy arrays measure temperature, salinity, and current speed at key locations in the Atlantic and beyond. Deep floats track the movement of water masses across basins. Satellite measurements provide surface temperature and height, revealing shifts in circulation patterns. Together, these tools indicate a slowing of the overturning circulation compared to mid-20th century estimates. While uncertainty remains in the magnitude and timing of changes, the trend is clear. Warming and ice melt are altering the flow of energy and mass through the ocean, with far-reaching effects on climate and ecosystems. Currents influence regional climate not only through heat transport, but also through moisture distribution. Evaporation from warm surface waters adds humidity to the atmosphere, affecting rainfall patterns. Disruption of currents changes where heat and moisture accumulate, shifting storm tracks and precipitation zones. Tropical regions may experience stronger monsoons or longer dry seasons. Mid-latitudes may encounter more frequent heat waves or cold snaps. Polar regions, while warming overall, may see uneven patterns of sea ice loss and local climate variation due to altered ocean circulation. The ocean's heartbeat, once a stabilizing force, now conveys new rhythms that interact with the atmosphere, producing changes that are both local and global. In the Pacific, the thermohaline circulation interacts with the El Niño Southern Oscillation. Changes in density and heat distribution influence the frequency and intensity of El Niño and La Niña events. These oscillations, in turn, affect rainfall, storm patterns, and temperature extremes across continents. Disrupted circulation in one part of the ocean can therefore influence weather thousands of kilometers away, demonstrating the global connectivity of currents. Similar interactions occur in the Indian Ocean and Southern Ocean, where seasonal and density-driven currents respond to warming and freshwater input. The ocean's pulse is a network of interdependent movements, each sensitive to small changes in heat and salinity. Warming alters the ocean's heartbeat. Thermohaline circulation, which moves heat and mass vertically and horizontally, is slowing in key regions such as the North Atlantic. The AMOC, a major component of this system, is weaker than in previous decades, influenced by warmer surface temperatures and freshwater input from melting ice. Currents such as the Gulf Stream and Kuroshio are affected, redistributing heat and nutrients differently than before. Regional climates respond to these changes, with impacts on temperature, precipitation, storm activity, and marine ecosystems. The ocean's pulse is shifting, reflecting both the energy humans release and the subtle, long-term response of the planet's largest moving system. Each change in the rhythm carries consequences, reminding us that the ocean is not a static backdrop, but a dynamic, global force that shapes life on Earth. The warming ocean is reshaping life beneath the waves. Species that once thrived in stable conditions are moving to find water that suits their needs. Fish, plankton, corals, and invertebrates respond slowly to the changing temperature, yet over time, entire ecosystems shift. Tropical fish expand poleward, following warmer currents, while cold water species retreat toward higher latitudes. These migrations are measurable in long-term surveys, showing that ocean warming is a direct driver of change. Species cannot always adapt quickly enough, and some face declining populations or local extinction when suitable habitat disappears. The oceans are dynamic, yet the speed of warming forces rapid adjustments in the distribution of marine life. Coral reefs illustrate the effects vividly. Corals rely on a symbiotic relationship with algae, which provide energy through photosynthesis. When water warms beyond a certain threshold, the corals expel the algae in a process called bleaching. Bleached corals are not dead immediately, but they become weaker, more susceptible to disease, and less able to reproduce. Repeated bleaching events reduce the structural complexity of reefs, affecting the thousands of species that depend on them. Observations at the Great Barrier Reef, the world's largest coral system, reveal a pattern of frequent bleaching in recent decades. Large-scale events in 2016, 2017, and 2020 caused significant mortality, particularly in the northern regions, demonstrating the sensitivity of corals to sustained temperature increases. The effects ripple through the ecosystem as fish and invertebrate populations respond to changes in habitat and food availability. Fish migrations respond to warming in measurable ways. In the North Atlantic, cod and other cold water species have shifted their distribution northward over the past 50 years. Long-term catch records show changes in species composition along continental shelves, reflecting the movement of fish toward cooler waters. Warmer waters in the south reduce growth rates and reproductive success, while northern areas, previously too cold, now provide suitable habitat. These shifts affect fisheries, altering the availability of species that communities depend on for food and economic activity. Fishermen must adjust to changing locations, and some regions experience declines in traditional target species. Observations indicate that these shifts are accelerating as warming continues, demonstrating a direct link between ocean temperature and species distribution. Plankton, which forms the base of the food chain, also responds to warming. Both phytoplankton and zooplankton are sensitive to temperature, light, and nutrient availability. Warming can stratify the water column, reducing nutrient upwelling from deeper layers. In areas where stratification increases, phytoplankton abundance may decline, altering the food available for zooplankton. These changes cascade up the food web, influencing fish, seabirds, and marine mammals. Satellite observations, combined with field measurements, show that plankton blooms are shifting in timing and location, particularly in temperate and polar regions. The result is a subtle, large-scale restructuring of marine ecosystems, driven by temperature-induced changes in primary productivity. Case studies provide detailed insight into these dynamics. At the Great Barrier Reef, coral bleaching is monitored annually. Surveys indicate that northern reefs experience the highest temperatures and most severe bleaching, while southern reefs, historically cooler, are beginning to face similar stress. The loss of coral cover reduces habitat complexity, affecting fish diversity. Some fish species move to deeper or cooler waters, while others decline locally. Reef-associated invertebrates, such as sea stars and crabs, also respond to habitat loss, with shifts in abundance and distribution. The ecosystem responds as a whole, with both immediate and long-term changes observable over decades of monitoring. In the North Atlantic, long-term fisheries data reveal shifting populations of cod, haddock, and other key species. Surveys indicate that spawning grounds have moved northward, and traditional fishing grounds now contain fewer cold water species. Warmer waters favor species previously found in more southern regions, changing the composition of catches. This redistribution affects not only ecological relationships, but also human communities dependent on fisheries. Management practices must adapt to these changes, and predictive models are used to anticipate future distributions based on temperature trends. The link between warming waters and shifts in species is clear, demonstrating the broader consequences for both ecosystems and human use. Coral bleaching interacts with other stressors, including acidification, pollution, and overfishing. While temperature alone can trigger bleaching, These additional pressures reduce the resilience of corals, slowing recovery and making repeated bleaching more damaging. The combination of warming and other stressors amplifies the changes in reef ecosystems, leading to declines in biodiversity and altered food webs. Observed responses include reduced fish abundance, changes in algal composition, and localized loss of habitat structure. These shifts illustrate the interconnected nature of marine ecosystems and the compounding effects of multiple stressors, all influenced by the rising temperature of the ocean. Fish species respond to warming not only by moving, but also by altering behavior and timing. Spawning events may occur earlier or later depending on the water temperature, affecting survival rates of larvae. Feeding patterns shift to match prey availability, which itself may have moved due to changing plankton distribution. Migration routes adjust to access suitable thermal habitats, and some species may shorten or extend their journeys. These behavioral adaptations illustrate the flexibility of marine life, but also highlight limits. Not all species can adjust quickly enough, and some may experience declines when habitat or prey become unavailable. Observational studies confirm these shifts across multiple ocean basins, revealing a widespread pattern of ecosystem change. Plankton responses are region-specific. In the North Atlantic, warming and stratification have reduced the spring bloom in some areas, while subtropical zones may see increased productivity due to longer growing seasons. These shifts affect fish larvae survival and seasonal food availability. In tropical regions, changes in plankton timing can influence reef fish and other organisms that rely on predictable cycles of food supply. The consequences propagate through ecosystems, altering predator-prey dynamics and influencing overall biodiversity. Observations using satellite imagery and water sampling show these subtle yet pervasive changes, linking ocean temperature directly to ecosystem structure. Marine mammals also respond to these ecosystem shifts. Species such as seals, whales, and dolphins depend on fish and plankton for food. As prey distributions move, predators must adjust migration routes and feeding locations. In some cases, competition for resources increases, while in others, food scarcity affects reproduction and survival rates. Warming waters can also influence breeding areas, particularly in polar regions, where sea ice retreat changes habitat availability. Observations of whale migration and seal breeding behavior reveal responses to these ecological changes, demonstrating the cascading effects of ocean warming on multiple levels of marine life. The cumulative effect of warming on marine ecosystems is substantial. Coral reefs lose complexity, fish redistribute, plankton abundance shifts, and predators adapt to new conditions. These changes are observable in the Great Barrier Reef, North Atlantic fisheries, and other monitored regions. Long-term records show that even small increases in temperature, when sustained over decades, lead to measurable alterations in species composition, behavior, and ecosystem function. The ocean's warming acts as a driver of continuous change, reshaping habitats and interactions in ways that ripple through entire food webs. The warming ocean forces marine life to adapt through migration, behavioral change, and altered growth patterns. Coral bleaching reduces habitat complexity and resilience, affecting thousands of species. Fish respond by moving toward cooler waters, changing the composition of local communities. Plankton abundance and distribution shift, altering the base of the food chain and influencing predators. Observed case studies, such as the Great Barrier Reef and North Atlantic fisheries, provide concrete evidence of these changes. The ocean is in flux, a dynamic system responding to heat, yet the pace of change challenges the ability of species to adjust, highlighting the interconnectedness of temperature, habitat, and survival beneath the waves. The ocean is not only a home for marine life, it is a driver of weather and climate across the planet. The heat stored in the ocean fuels storms, influences winds, and shapes rainfall patterns. As the ocean warms, more energy enters the atmosphere, altering the intensity and frequency of weather events. Hurricanes, typhoons, monsoons, and even seasonal cycles like El Niño and La Niña respond to changes in ocean temperature. The connection is direct. Warmer water contains more energy, which can be transferred to the air above, feeding clouds, rain, and wind in ways that affect millions of people. Scientists observe these changes with a combination of satellite data, ocean buoys, and climate models, confirming that the ocean's temperature is a central factor in global weather. Hurricanes derive their power from warm surface water. The tropical oceans act as heat reservoirs, storing energy that storms can tap into. When water temperatures rise above about 26 degrees Celsius, the conditions become favorable for hurricane formation. Warmer water allows storms to intensify more rapidly, producing stronger winds, heavier rainfall, and higher storm surges. Observational data show that the intensity of the strongest hurricanes has increased over the past decades, linked directly to higher sea surface temperatures. Hurricanes are more than localized events. They redistribute heat and moisture across the ocean and atmosphere, influencing weather far beyond their immediate path. Warming oceans supply additional energy, increasing the potential destructiveness of these storms. Monsoons, particularly in South and Southeast Asia, are closely tied to ocean temperature. Seasonal shifts in heating between land and ocean drive the movement of air masses, producing wet and dry seasons. When the ocean is warmer than usual, the monsoon circulation can intensify, bringing heavier rainfall. In some years, monsoons may arrive earlier or later, or shift in strength across regions. These changes have direct consequences for agriculture, water resources, and human communities. Observations of rainfall patterns indicate that warming oceans are contributing to more variable and extreme monsoon seasons, with stronger wet periods and prolonged dry periods, creating challenges for ecosystems and people alike. The Pacific Ocean, through the El Niño Southern Oscillation, exemplifies the connection between ocean temperature and global weather. During El Niño events, the eastern tropical Pacific warms, altering atmospheric pressure patterns and shifting wind currents. This change affects rainfall and temperature across Asia, the Americas, and Africa. La Niña events, in contrast, involve cooler than average surface temperatures in the same region, producing nearly opposite effects. As the ocean warms overall, the frequency, intensity, and regional impacts of these events may change. Scientific studies suggest that warmer baseline temperatures enhance the effects of both El Niño and La Niña, amplifying floods, droughts, and storms in affected regions. These cycles illustrate how subtle shifts in ocean heat content influence weather on a planetary scale. Feedback loops between the ocean and atmosphere magnify the effects of warming. As surface waters heat, evaporation increases, adding moisture to the air. This additional moisture can fuel storms, produce heavier rainfall, and change cloud formation. Warmer water also affects atmospheric pressure, altering wind patterns and the movement of weather systems. In turn, the atmosphere can influence the ocean through wind-driven currents, upwelling, and the distribution of heat. These interactions form continuous feedback loops, with the ocean and atmosphere responding to each other in real time. The loops are complex but measurable, demonstrating that ocean warming does not act in isolation but as part of an interconnected climate system. The Atlantic Ocean influences hurricanes not only in the tropics but also in regions far north. Warm waters along the Gulf Stream and the Caribbean provide energy for storms that travel toward the United States, the Caribbean islands, and beyond. Observations show that when the ocean is warmer than average, storms intensify more quickly and retain strength farther north than in cooler years. This is particularly evident in late-season hurricanes, which can develop and persist in regions that historically experienced weaker storms. Data indicate a correlation between rising sea surface temperatures and the number of Category 4 and 5 hurricanes, confirming that energy stored in the ocean translates into stronger extreme events. Storm surge, the rise of seawater above normal tide levels during hurricanes, is also influenced by warming. Higher sea levels caused by thermal expansion and ice melt allow storm surges to penetrate further inland. Combined with stronger winds and heavier rainfall, this creates more damaging events. Observational records from coastal areas demonstrate that the combination of rising ocean heat and elevated sea levels is increasing the risk of flooding and property damage during tropical storms. The warming ocean thus amplifies multiple aspects of storm impact, from intensity to reach, with direct consequences for human and ecological systems. El Niño events can trigger cascading effects in distant regions. Warmer tropical Pacific waters reduce upwelling along the west coast of South America, affecting nutrient availability and fisheries. In the atmosphere, shifts in pressure and wind patterns lead to altered rainfall and temperature in Southeast Asia, Africa, and North America. During strong El Niño years, some regions experience drought, while others receive above-average rainfall. La Niña events produce nearly opposite patterns, with some regions benefiting from increased precipitation while others face aridity. Studies suggest that overall ocean warming may increase the variability of these cycles, producing more extreme weather events on both ends of the spectrum. The ocean's energy shapes conditions thousands of kilometers away, demonstrating its global influence. The Indian Ocean responds to both local warming and remote influences from the Pacific. Warmer waters enhance evaporation, contributing to monsoon rainfall and the distribution of tropical storms. Feedback loops operate here as well. Wind-driven circulation distributes heat, influencing both the timing and strength of rainfall across South and Southeast Asia. As surface temperatures rise, rainfall patterns become more variable, with both stronger wet periods and longer dry spells. This variability has ecological consequences, affecting river flow, wetland ecosystems, and agricultural productivity. The ocean's thermal energy drives these changes, connecting water temperature to life on land in a continuous chain of cause and effect. Regional temperature differences influence atmospheric circulation on a global scale. Warming in the tropics affects the Hadley cell, the large-scale movement of air between the equator and subtropics. The cell carries moisture and heat from tropical regions toward higher latitudes. Changes in ocean temperature alter the speed and intensity of these movements, affecting rainfall patterns across deserts, monsoon regions, and mid-latitude storm tracks. Observations suggest that warming oceans modify the positioning and strength of these cells, with implications for weather and climate stability. The ocean acts as a heat engine, driving air, movement, and determining how energy and moisture are distributed across the planet. Extreme precipitation events are more likely as ocean temperatures rise. Warm water increases evaporation rates, adding moisture to the atmosphere. When this moist air rises and cools, it condenses to form clouds and rainfall. The additional energy from the ocean allows for heavier downpours and longer-lasting storms. Observational records indicate an increase in extreme rainfall events in regions with warming seas. These storms can cause flooding, soil erosion, and damage to infrastructure. The process demonstrates the direct link between ocean heat content and the hydrological cycle, emphasizing the role of the ocean as a regulator of water movement and distribution. The atmosphere, in turn, affects the ocean. Wind patterns influence upwelling and mixing, redistributing heat and nutrients. Changes in storm frequency or intensity can mix surface waters, temporarily cooling some areas while warming others. El Niño and La Niña cycles modify the strength and direction of trade winds, altering the distribution of warm and cold water. These interactions illustrate a continuous exchange of energy between the ocean and atmosphere, where warming affects weather, and weather in turn influences ocean conditions. The feedback is ongoing and complex, yet scientists can observe and model the main patterns with growing accuracy. The warming ocean influences weather and climate by adding energy to the atmosphere, fueling hurricanes, altering monsoon patterns, and modifying El Niño and La Niña cycles. Increased ocean heat leads to stronger storms, heavier rainfall, and shifting rainfall patterns with measurable effects across continents. Feedback loops between the ocean and atmosphere amplify these changes, creating continuous interaction between heat, moisture, and air movement. Observations and models confirm that ocean warming directly connects to extreme weather and climate variability, showing that the energy stored in the seas shapes life, safety, and ecosystems on a global scale. The ocean's heat is both a driver and a messenger, revealing the profound links between water, air, and life on Earth. As the ocean warms, it holds less oxygen. This is a basic property of water. Warmer water cannot contain as much gas as colder water. Oxygen is vital for marine life. Fish, invertebrates, and even microscopic plankton rely on dissolved oxygen to survive. As temperatures rise, the amount of oxygen available decreases, affecting the health and behavior of organisms throughout the water column. Observations from long-term monitoring stations show a gradual decline in dissolved oxygen in many regions, particularly in tropical and subtropical waters, where warming has been most pronounced. The decline is subtle but continuous, influencing life in ways that are not always immediately visible but become clearer over time. Oxygen minimum zones form where low oxygen concentrations create challenging conditions for marine life. These zones typically develop in the mid-depth layers of the ocean, often between 100 and 1,000 meters, where oxygen consumption by organisms and decomposition of organic matter exceeds the supply from surface waters. Warming intensifies these zones. As surface waters heat, they become less dense and less able to mix with deeper layers, reducing the vertical transport of oxygen. At the same time, higher temperatures accelerate metabolic rates of organisms, increasing their oxygen demand. This combination leads to expanded and intensified oxygen minimum zones, affecting species adapted to specific oxygen ranges. The expansion of oxygen minimum zones has direct consequences for marine species. Many fish, squid, and invertebrates are adapted to narrow oxygen conditions. In areas where oxygen drops, organisms must migrate to find suitable habitat or face stress and mortality. Vertical migration, often a daily movement between deep and surface waters, becomes more difficult when oxygen is low. Some species are forced into shallower waters, where competition for space and food increases. Others may retreat to regions where oxygen remains sufficient, altering predator-prey relationships. Long-term observations indicate that changes in oxygen concentration already influence species distribution, particularly in regions like the eastern tropical Pacific and the northern Indian Ocean. Deep-sea species are especially vulnerable. These organisms live in stable, low-oxygen environments, often adapted to very limited metabolic rates and slow growth. Warming and the associated oxygen decline reduce their capacity to survive. Many deep-sea species cannot migrate rapidly to new habitats. Their slow reproduction rates and specialized adaptations make recovery from stress slow. Observations from oxygen minimum zones show declines in abundance and changes in community composition over time. Species that once thrived at mid-depths may disappear locally, replaced by more tolerant organisms. The deep ocean, once considered a refuge from rapid environmental change, is increasingly affected by warming and oxygen loss. The eastern tropical Pacific provides a clear example. In this region, a naturally low oxygen layer exists between surface and deep waters. Warming of the surface ocean reduces mixing, while increased biological activity consumes more oxygen at depth. Over recent decades, measurements indicate that this oxygen minimum zone has expanded both vertically and horizontally. Fish species such as anchovies and sardines are forced to shift their depth range or migrate to adjacent areas. The movement alters predator-prey interactions and affects fisheries dependent on these species. Even small changes in oxygen concentration influence the structure of marine communities, highlighting the sensitivity of ocean life to thermal and chemical changes. The Arabian Sea demonstrates similar dynamics. Seasonal monsoon winds drive productivity, producing high biological activity near the surface. When organic material sinks, decomposition consumes oxygen at mid-depths. Rising temperatures reduce the solubility of oxygen and slow vertical mixing, expanding the oxygen minimum zone. Observations show that species such as lanternfish, which occupy these layers, experience increased stress. Reduced oxygen can also influence reproductive success, with larvae and juveniles particularly vulnerable. The expansion of oxygen-depleted water alters food webs, affecting not only mid-water species, but also predators like tuna and sharks that depend on them. Oxygen decline interacts with other aspects of warming. Warmer waters reduce the solubility of oxygen and accelerate metabolic rates, while changes in currents and stratification limit replenishment from deeper or surface waters. In coastal regions, nutrient runoff can exacerbate oxygen depletion. Excess nutrients stimulate phytoplankton growth, which, upon decomposition, consumes additional oxygen. The combination of warming and nutrient input produces seasonal or persistent hypoxic conditions, sometimes resulting in localized dead zones where oxygen levels are too low to support most marine life. Observations in areas such as the Gulf of Mexico show that these processes have intensified over recent decades, affecting fisheries and coastal ecosystems. The loss of oxygen affects species behavior. Fish and mobile invertebrates detect low oxygen and move toward oxygen-rich areas. These migrations concentrate populations in smaller regions, increasing competition for food and space. Predators may find prey more easily, but the overall health of the population can decline due to stress and limited habitat. Some species reduce activity to conserve oxygen, slowing growth and reproduction. Laboratory and field studies demonstrate that oxygen stress alters feeding, swimming, and reproductive behavior, with long-term consequences for survival and ecosystem function. Even minor declines in oxygen concentration can have measurable impacts on species performance. Plankton are influenced by oxygen changes as well. Zooplankton, which often migrate vertically daily, may encounter low oxygen layers that restrict movement. Phytoplankton growth near the surface may continue, but the decline in oxygen at mid-depths affects the cycling of nutrients and the availability of food for mid-water species. The result is a cascading effect through the food web. Predatory fish and larger organisms experience indirect consequences as the abundance and behavior of prey change. Observations in tropical and subtropical waters reveal altered vertical distributions of plankton, linking oxygen decline to broader ecological changes. Expansion of oxygen minimum zones has global implications. As low oxygen water spreads, the area available for habitable ocean decreases. This limits the capacity of the ocean to support marine life, particularly in the mid-depth layers that were once rich in species diversity. The shift affects nutrient cycling, carbon sequestration, and overall productivity. Reduced oxygen alters decomposition rates and microbial activity, influencing the breakdown of organic material and the release of greenhouse gases. The ocean, a central component of the Earth's climate system, responds in multiple interconnected ways to warming and oxygen decline, demonstrating how one physical change can cascade into chemical and biological effects. Polar regions also experience oxygen stress, though in different ways. Cold water holds more oxygen than warm water, but warming at high latitudes reduces solubility and contributes to stratification. Meltwater from glaciers adds a layer of low salinity water at the surface, reducing mixing and oxygen replenishment at depth. In the Arctic and Southern Ocean, species adapted to high oxygen cold water may face stress as their environment warms and oxygen declines. Observations indicate that some fish, squid, and invertebrates are shifting depth or latitude, tracking suitable oxygen conditions. The consequences extend to top predators, such as seals and whales, that rely on mid-depth prey for feeding. Long-term monitoring confirms the trends. Sensor arrays, floats, and ship-based surveys measure oxygen concentration, temperature, and salinity across ocean basins. Data show consistent declines in dissolved oxygen in tropical and subtropical regions, expansion of oxygen minimum zones, and localized hypoxia in coastal areas. Deep-sea surveys revealed changes in species composition in regions affected by low oxygen. These observations support models predicting continued expansion of oxygen-depleted zones as warming persists. The ocean's capacity to sustain life is closely linked to temperature, circulation, and oxygen content, highlighting the vulnerability of marine ecosystems in a warming world. Ocean warming reduces oxygen solubility, expands oxygen minimum zones, and stresses marine life, particularly in mid-depth and deep-sea habitats. Fish, invertebrates, and plankton respond by migrating, altering behavior, or experiencing declines in population. Observed case studies in the eastern tropical Pacific, Arabian Sea, and coastal dead zones illustrate these changes. Oxygen decline interacts with warming, stratification, and nutrient cycles, creating cascading effects on ecosystems and productivity. The ocean's ability to support life is tied to its oxygen content, and as warming progresses, these low oxygen zones grow, highlighting the interconnected and fragile nature of marine systems. The warming ocean affects human communities as directly as it does marine life. Rising seas, stronger storms, and shifting fish populations change the way people live along coasts. Coastal flooding is becoming more common, particularly in low-lying regions, where small increases in sea level translate into frequent inundation. Storm surge, fueled by warmer waters, pushes seawater further inland during hurricanes and typhoons, causing damage to homes, infrastructure, and farmland. Observations from cities like Miami, Jakarta, and Dhaka show repeated flooding during high tides, even without storms, indicating that gradual sea level rise is altering daily life. The connection between ocean heating and human risk is clear. As the ocean warms, the land it borders becomes increasingly vulnerable. Fisheries are affected by the combined pressures of warming, oxygen decline, and species migration. Communities that rely on local fish populations may find catches declining or changing in composition. Traditional fishing grounds may no longer yield familiar species, forcing fishermen to travel further or switch to different types of catch. The collapse of certain fisheries has already been observed in regions like the North Atlantic, where cod populations shifted northward, and in the tropics, where coral reef fisheries declined following bleaching events. This disruption affects food security, particularly in regions where fish is a primary protein source. The ocean, once a reliable provider, is now less predictable, requiring humans to adapt quickly. Economic consequences are widespread. Coastal property values can decline due to repeated flooding and storm damage. Tourism, often reliant on beaches, coral reefs, and clear waters, suffers when these features degrade. Infrastructure such as ports, roads, and energy systems face damage and increased maintenance costs. Insurance premiums rise as risk grows, and some communities struggle to recover after repeated events. Observational records show that both direct damage from storms and gradual losses from sea level rise contribute to long-term economic stress. The human and economic cost of a warming ocean is therefore cumulative, affecting livelihoods, trade, and regional stability. Displacement is a growing concern. In low-lying coastal areas, residents are forced to relocate as flooding, erosion, and storm damage increase. Island nations such as the Maldives and Tuvalu face existential threats as sea level rise encroaches on habitable land. Even in larger countries, densely populated delta regions like the Ganges-Brahmaputra or Mekong face repeated inundation, displacing millions over time. Relocation can disrupt social networks, education, and employment, creating additional pressures beyond immediate physical danger. Human migration patterns are increasingly linked to ocean-driven environmental change, illustrating the direct influence of warming waters on societal structures. Food security is affected not only by reduced fisheries, but also by changes in coastal agriculture. Saltwater intrusion from rising seas contaminates freshwater supplies and soils, reducing the viability of crops near the coast. Combined with stronger storms and altered rainfall patterns, these changes threaten the productivity of coastal farms. Communities dependent on both fishing and farming face a dual challenge, with the ocean's heat altering two critical food sources simultaneously. Observational data from coastal Bangladesh, Vietnam, and parts of West Africa confirm declining crop yields in areas experiencing sea level rise and increased storm frequency. The ocean's energy reaches inland through water and soil, demonstrating the interconnectedness of marine and terrestrial systems. Human adaptation takes multiple forms. Coastal defenses, such as seawalls, levees, and breakwaters, are constructed to protect communities from flooding and storm surge. These structures can reduce damage in the short term, though they often require ongoing maintenance and can alter local ecosystems. In some areas, living shorelines using mangroves, salt marshes, and other natural barriers provide protection while supporting biodiversity. Observations indicate that mangroves can reduce wave energy significantly, protecting both property and fish habitats. Coastal planning increasingly incorporates both hard and soft defenses, aiming to balance protection with environmental sustainability. Fisheries management is also adapting. Regulations on catch limits, protected areas, and seasonal closures help sustain fish populations under changing conditions. Shifts in species distribution require flexible management strategies, as traditional territorial boundaries for fishing may no longer align with where fish are found. Observational data show that adaptive management can mitigate some impacts of species migration, supporting livelihoods while maintaining ecological balance. In some regions, international agreements allow for coordinated management across borders, reflecting the global nature of the ocean and the shared dependence on its resources. Early warning systems for storms and flooding are vital for reducing human risk. Meteorological networks, satellite data, and ocean buoys provide real-time information on approaching hurricanes, storm surges, and high tides. Communities use these systems to evacuate, protect property, and coordinate response. Observational evidence indicates that effective warning systems reduce casualties and property loss, demonstrating the value of monitoring and communication in a warming world. The ocean's behavior can be anticipated to some degree, but preparedness and response remain critical to minimizing harm. Urban planning increasingly considers ocean-driven risks. Coastal cities are elevating infrastructure, redesigning drainage systems, and zoning areas for resilience. Flood-prone neighborhoods may be reinforced or relocated, and building codes adjusted to account for storm surge and sea level rise. Observations from cities such as Rotterdam and New York City show that integrating climate data into urban planning reduces vulnerability over time. Human settlements must respond dynamically to changes in the ocean, reflecting a continuous dialogue between society and the environment. Insurance and economic instruments help communities cope. Risk assessment models that incorporate sea level projections, storm frequency, and ocean heat content inform pricing and coverage decisions. In some regions, government support, subsidies, or relocation assistance mitigate financial impacts on vulnerable populations. Observational studies demonstrate that well-planned economic adaptation can maintain stability even as environmental conditions shift, linking human resilience directly to knowledge of ocean changes. ecosystem-based adaptation also plays a role. Protecting and restoring habitats such as mangroves, coral reefs, and wetlands provides natural buffers against storms while maintaining biodiversity. These habitats absorb wave energy, reduce flooding, and support fisheries that communities rely on. Observations show that areas with intact coastal ecosystems experience lower damage from storm surge and flooding. The integration of natural and engineered solutions illustrates the importance of understanding ocean dynamics in human adaptation strategies. Long-term planning requires an understanding of both local and global ocean changes. Sea level rise, storm intensity, and species migration are influenced by warming that originates far from the coast. Collaborative monitoring and modeling provide insights into future risks, informing policy and infrastructure development. Coastal communities, governments, and international organizations use these data to prioritize investment and prepare for projected changes. The ocean's heat content is therefore not only a scientific measurement, but a tool for practical decision-making, guiding human adaptation to a changing environment. Warming oceans directly affect human populations through coastal flooding, storm surge, and changing fisheries. Socioeconomic effects include displacement, reduced food security, and economic stress. Adaptation measures such as coastal defenses, fisheries management, early warning systems, and ecosystem restoration help mitigate some impacts. Observations across the globe, from low-lying islands to major coastal cities, demonstrate that human communities are intimately connected to ocean conditions. The warming ocean is both a challenge and a force that requires careful planning, cooperation, and resilience, highlighting the dependence of society on the stability of marine systems. Humans respond, adapt, and plan, but the changes underway emphasize the central role of ocean heat in shaping both ecological and human futures. The ocean continues to absorb heat at a pace that exceeds early predictions. Scientific measurements reveal that the top layers of the ocean are warming more rapidly than previously thought, while deeper layers show a slower but steady increase in temperature. Satellites, autonomous floats, and research ships monitor these changes, recording not only surface temperatures, but also the distribution of heat. Through the water column, models project that if current greenhouse gas emissions continue, the ocean's heat content will rise significantly over the coming decades, storing more energy than the atmosphere. This heat accumulation drives many processes, from storm intensity to sea level rise, making the ocean both a buffer and a signal of planetary change. Sea levels are projected to rise steadily as a result of both thermal expansion and ice melt from Greenland and Antarctica. Thermal expansion occurs because water expands as it warms, adding volume even without the addition of new water. Melting ice sheets contribute further, adding mass to the ocean. Observational records show that sea level has risen more than 20 centimeters since the late 19th century, with recent decades showing accelerated increases. Projections indicate that by the end of this century, seas could rise by 0.5 meter or more under high-emission scenarios. Even moderate increases pose challenges for coastal communities, ecosystems, and infrastructure, emphasizing the scale of adaptation required. Ocean warming is not uniform. Polar regions warm faster than the tropics, while some parts of the Pacific and Atlantic show accelerated heat absorption. Local variations are influenced by currents, wind patterns, and circulation systems, which redistribute heat and interact with regional climates. Monitoring these patterns allows scientists to refine projections, but uncertainties remain. Deeper layers of the ocean are less well sampled, and long-term trends depend on consistent global observations. Despite these limitations, the overall trend is clear. The oceans are warming at an unprecedented pace, storing energy that will influence climate and weather for centuries. Climate models provide estimates of future ocean conditions, but have inherent limitations. While they incorporate physical laws, observations, and historical data, they cannot capture every detail of ocean circulation, biological feedbacks, or regional variability. Some processes, such as the response of deep ocean currents or ice sheet dynamics, are complex and only partially understood. Monitoring networks are expanding, but gaps remain, particularly in remote or deep regions. These limitations mean projections carry uncertainty, yet the overall trajectory, continued warming, rising seas, and shifts in ecosystems is robust across models. Understanding these limits is essential for interpreting forecasts and preparing for future change. Urgent emissions reductions remain critical to limiting further ocean warming. Carbon dioxide and other greenhouse gases trap heat in the atmosphere, which ultimately moves into the ocean. The more we emit, the faster the ocean warms, and the greater the associated impacts on ecosystems, sea level, and human communities. Mitigation through reduced fossil fuel use, renewable energy adoption, and carbon sequestration can slow the rate of warming. Even modest reductions in emissions can influence the trajectory of ocean heat content over decades. Observations from recent decades show that regions where emissions growth slows or declines can experience measurable benefits in oceanic and atmospheric conditions. The ocean's response is slow but persistent. Heat absorbed today continues to influence circulation, chemistry, and biology for decades or centuries. The vastness of the ocean means that changes are often subtle, unfolding over long timescales. Surface warming may be evident seasonally or annually, but the deeper waters respond gradually, accumulating heat and affecting oxygen content, currents, and ecosystems in ways that are not immediately visible. Scientists emphasize the importance of long-term monitoring, as short-term fluctuations may mask the underlying trend of sustained warming and its cumulative effects. As the ocean warms, it continues to shape the world in ways that touch every continent. Storms draw energy from its heat, monsoons are altered, and species distributions shift. Ice melt and thermal expansion raise sea levels, while oxygen decline affects marine life. The slow but persistent changes remind us that the ocean is a living system, interconnected with the atmosphere, land, and human society. Observations show that even remote areas, far from human settlements, are affected. The ocean's enormity and reach connect distant regions, illustrating the planet's integrated nature and the importance of understanding its changes. Sensory reflections help convey the scale of the ocean's influence. Imagine standing on a quiet shore as the sun sets, feeling the warmth of the breeze that has absorbed the ocean's heat, hearing the distant hum of waves that circulate energy across the globe, and sensing the rhythm of tides influenced by both the moon and the thermal expansion of warming waters. Beneath the surface, currents move slowly but relentlessly, carrying heat, nutrients, and life across vast distances. Life forms, from microscopic plankton to large whales, respond to these changes, moving, feeding, and reproducing within a system that is immense, yet sensitive to subtle shifts in temperature and chemistry. The ocean teaches patience and perspective. Its changes occur over decades, yet their cumulative effects are profound. Each degree of warming has consequences for storms, sea levels, oxygen availability, and ecosystems. Each small rise in sea temperature shifts currents, migratory patterns, and the distribution of species. The ocean's slow persistence contrasts with the rapid pace of human decisions, highlighting the need for careful, informed action. Scientists study temperature profiles, circulation patterns, and ecosystem responses to understand the trajectory of change, providing a foundation for adaptation and mitigation. Ultimately, the ocean's story is ongoing. Observations and models indicate that warming will continue unless emissions are reduced. Sea levels will rise, storms will intensify, and marine ecosystems will continue to shift. Yet the ocean also holds the potential for resilience. Healthy, well-protected ecosystems, careful management of resources, and reduced human impact can help buffer communities and species from the worst outcomes. The persistent, enormous, and interconnected nature of the ocean emphasizes both our dependence on its stability and the responsibility to act thoughtfully in response to its changes. Looking ahead, the ocean reminds us of scale, time, and connection. From the surface to the deep, from tropical waters to polar seas, heat is stored and redistributed, shaping the environment slowly yet continuously. Life adapts, storms form, and communities adjust, all in response to the ocean's influence. By understanding these processes and observing their ongoing changes, humans gain insight into both the limits and possibilities of adaptation. The ocean, vast and patient, continues to reflect the energy we put into the climate system, urging awareness, action, and respect for the slow, persistent rhythm of planetary change.